travels towards the Stratosphere of Infinities. So in today's lesson, we're going to attack the question of, is there an infinity with a greater cardinality than the real numbers? Well, let's get started. To work at this problem, we need to first understand a few basic things about set theory. And a set can be a collection of any objects. Now in math, oftentimes we represent them like this. We say a set is defined as saying an S to represent the set, and it's a capital letter S, is equal to, then we have these braces or parentheses, whatever you wish to call them, but it's recognized internationally as this symbol. And then inside it, you list all of the elements of the set. An element and a member are basically the same thing. This set S has 3 members in it. It has 3 elements in it. Everything that's inside of it is considered an element or a member. There is another thing in set theory called a subset. So if you have a set and you take things from that set and put it in a second set, the second set is considered a subset of the first set. So if we have our set S, which has elements A, B, and C in it, and we take out, for example, just A, well, the set of A would be considered a subset. A subset is always a set, so it'll have these brackets on them. Now, it could also be taking more than one thing from it. It could be, for example, taking A and C from the set, and the subset is made up of elements from the original set. If you have a set and you take nothing from the set and put that nothing in a set, well, then it's an empty set, right? It's also referred to as the null set. So a set of brackets with nothing inside of it is referred to it as the empty set or the null set. In different math books, it's also written as you see here. That's probably a little bit more common, but I'll use the empty brackets because the book uses that. And so, as you might guess, but it's also a little bit surprising, the empty set or the null set is a subset of every set. After all, as this kind of hinted at before, you can take nothing from a set, even if it's the empty set. You can take nothing from it and put it in a subset, and it just would be the empty set as well. The other thing that is sometimes surprising for students is that the entire set itself is also a subset of itself. So, if I have set S, I can take everything out of it and put it in a subset, and it would be the entire set. But it's referred to as a subset because we got it from the initial set. The power set is a term that refers to all of the possible subsets of a particular set. So, you can say the power set is a set of all subsets of a set, just because it's kind of fun to say. It's written with a cursive letter P, capital letter P, and looks like this. And so if we have a set S, which is made up of A, B, and C, what would the power set of S be? Well, we start off with this cursive letter S, so we know that what we're listing here is the power set. And we have an opening bracket because it is a set itself. It's a set of all of the subsets. So we'll have an opening and closing brackets for this. Now, usually what I do, at least what I like to do in keeping track of did I get all the possible subsets, is I start with the smallest. And of course the smallest subset is going to be the empty set. It is the empty set is a subset of every set, so it's going to be a subset of this. And it has no elements in, so we're starting with all of the sets that have 0 elements in. Then I like to go and take all of the subsets that have 1 element in it and build it up this way just to make sure I didn't forget something. So I would put in the set of A, because it has 1 element, the set of B, and of course the set of C. Now I've put in all of the possible subsets that have 1 element in, so I move on to all the possible subsets that have 2 elements in it. So I go back and take 2 elements from the original set. So I can take A and B, I can take A and C, and I can also take B and C. And I think about it, say there's no other possible combinations that work. In sets, so also in power sets, the order is not important. The set of A and C is the same thing as the set of C and A. Apple. Actually, for example, if you had an apple and a carrot, well, that's the same thing as having a carrot and an apple. So in sets, the order is not so important. Now, okay, so now we're back to our making the power set. We have all of the possible elements that, subsets that have 2 elements in it. So we go up to the next one, all the sets that have 3 in it. Since the set itself is a subset of itself, we also list the entire set there. Obviously, we don't have more than 3 elements, so we have to stop it there. So we put the closing parenthesis or bracket on the end. So that's a way to build it to make sure that you don't miss these. Nice little hint for any quiz or exam coming up. You can make sure you've got them all if you use this method. But if you have another method you want to use, that's fine as well. Now, if you wanted to find out how many elements are in any given power set, let's compare. Let's start with the set that has 1 element in it, the set Q that has the ampersand sign in it. Well, the power set is going to be, again, we start with 0 members. The null set, move on to members that have 1 element in it. Well, of course, that's the set itself, so the ampersand. If we look at set R that has 1 and 2 in it as elements, well, then we start again with the empty set, the sets that have 1 in it, and the sets with 2 in it, and list it there. And we go back to our set S that has 3 in it, and we know that it appeared like this. Now we can look at the relationship. Q had 1 element in it, and its power set had 2 elements in it. R has 2 elements in it, and its power set has 4 elements in it. And when we look at set S, we know that it had 3, and if we count them there, 1, 2, 3, 4, 5, 6, 7, 8. And there's 8 elements in the power set. So let's take these numbers and put them in a little bit nicer way to look at it. So in the first set that had 1 element in it, there was 2 in the power set. When there was 2 in the set, there was 4, and when there was 3 in the set, there was 8. Well, we kind of look at this and say, hey, this is kind of familiar to the rice and the checkerboard kind of thing. So we realize that 2 is 2 to the first, 4 is 2 squared, or 2 to the second, and 8 is 2 to the third. Well, wow, okay, well, that seems pretty simple. When elements have 1 in it, it's 2 to the first. When there's 2 elements in it, it's 2 squared. And there's 3 elements in it, it's 3 cubed, or 2 to the third. Excuse me, not 3 cubed. 2 cubed and 2 to the third. Well, then we realize that if it had n elements in it, it would have 2 to the n elements in it. And that is the definition of it. How many elements are in a power set? Well, the answer is 2 to the n, where n is the number of elements in the set. So if we had a set that had 8 elements in it, the power set would have 2 to the 8th. Don't worry, I won't ask you to write a power set that large in any quiz or exam that we have. Now, looking here at set S, we realize that the power set of S would have 2 elements in it, namely the empty set and the set of A. Well, if the power set is a listing of all of the subsets of a set, can we take the power set of the power set? Well, yeah, if it's simply taking a list of all possible subsets, the power set of S has in 2 elements of it, so we can take the power set of a power set. It would look a little bit like this. It's a little bit strange, but we'd say that the power set of S is equal to this. Now, the original set I have in red so that you can see. So it's, excuse me, it's going to be, again, the empty set, and then the set of all the elements with 1 in it. Well, the empty set is a set. So you put that inside of a set and say that it's going to be the set of the null set. And then you have the set of A, and then you have the set that consists of 2 elements of the null set and the set of A. Well, excuse me. Can we take the power set of the power set of a power set? Sure we can. Well, the power set of the power set of the power set of S is going to be, again, the empty set, or the null set, And then we're going to start with the power set that have one elements in. So it's going to be the set of the empty set, the set of the empty set, and the set of the set of the set of A, and this is going to just continue on for a long time. And it gets really kind of hairy. Starting the second line there, the set of the null set and the set of A. And this continues on. And like I said, it gets kind of hard. And do we really want to? Well, probably not. Could we take the power set of the power set of the power set of the power set of S? Yes, we could. But we don't really want to. It's confusing, right? It gets kind of hairy. Now, if we look at the sizes of these, how do these sizes compare? Well, obviously, if we started with the power set that was smaller, and we take the power set of the power set, that's going to be bigger. So we start with set S, it had one element in. The power set of S had two elements in it. The power set of the power set, well, since it had two elements, it's 2 to the 4th. It's going to be bigger. And we continue this. So the set is, or if you look at it, the set number in the set is smaller than the power set of the set, which is smaller than the power set of the power set of S, which is smaller than the power set of the power set of the power set of S. And this could continue on infinitely, right? Well, can we apply this to infinity? If we have the naturals, and we know that a set that has a greater cardinality than the naturals is the reals, what could have a greater cardinality we think of as being bigger than the real numbers themselves? Well, the power set of the power set is bigger, right? And the power set of the set is bigger. So maybe we should try using the power set of the reals. That should be bigger than the reals. Well, how do we do this? Well, Cantor came up with a way. It's called Cantor's power set theorem. And what he did is he made a one-to-one correspondence. He paired one element from the reals with one element from the power set of the reals. And then to show that there was not a one-to-one correspondence, he first asked two questions. Of this one-to-one correspondence, the first question he said is the element that I just picked here from the real numbers, the original set, is it inside of the power set that I paired with it? And then he asked the second question, do I want to include this in my set? We're doing a similar kind of thing where we're going to list everything on a list and make a one-to-one correspondence from here to infinity. And the one list is going to be the reals, and the second list is going to be the power set of the reals. So we list all possible combinations with that, and we're going to go through this and find a way that regardless of how many times we try it, regardless of what we do, we'll always find an element of the power set that's not in the original pairing that we set up. And every time we do it, whether we do it once, twice, or an infinite number of times, we'll always find another set that's not. So that would mean that the power set of the reals has a greater cardinality than the power set of the reals, or than the set of the reals itself. So his resulting subset is in the power set because it's a subset of them, a subset of the original set of the reals, but it's not in the one-to-one pairing. So there will be more in the power set. And hopefully that makes sense when we look at the finite. The power set is always bigger than the original set. Now, how did he do this? Well, it's kind of complicated, but if we look at it in the finite first, then it's easier. So what we do is we make a one-to-one pairing. I'm going to start with the finite set T here. Let's abbreviate the heart of math from your textbook. I just made it a little bit easier and just call it heart of math. So we list all of the elements of T in the first column. The second column is the elements of the power set. So we can pick any element of the power set. We can pick the empty set, we can pick the word of, we can pick the word heart, we can pick two words of and math, or heart and math. Or we could pick all three of them, and any of these. And so we pick as many of these as we have elements of T. Now obviously, we know that there are more subsets. After all, the subset of just the set of is a subset. It's not listed there. by itself. The null set is not listed there. The set with all three words is not there. So we know that there's more. When we do infinity, we also know that there's more, but we can't prove it, and we have to be able to prove it. So we go through this. Now, what Cantor does is he asks the question of the one pairing. So we look at the first one, the element of T is heart, and it's paired with the element of the power set that's the set of the word heart. And we do that one-to-one pairing for every element of T to an element of the power set. And we ask the question, is the element, the word heart, paired, is that inside of the subset or the element of the power set, which is of course a subset? But we look at that and say, okay, I'm going to make a set, and I ask this question, is the element in its paired subset of the power set of T? So we look, is the word heart in the subset it's paired with? Well, yes, it's right there. Heart is inside the second column. So yes, it is. Do I want it in my set? Well, what Cantor does here is he always chooses the opposite of the answer to the first question. So this one is paired there, so do I want it in my set? No, I do not. We go to the second one. The element of T is the word of. Is the word of inside of its paired element of the power set? Well, this paired element of the power set is just math. So we say, no, of course not. The word of does not appear in the set of math. Well, then we ask ourselves the second question. Do I want it in my set? We always do the opposite of what we just answered. So we said no. So yes, I want it in my set. So now I put the word of in my set. Now we go to the word math. Is the word math in its paired element of the power set of T? Well, no, it's not, right? So do I want it in my set? Yes, you do the opposite. So I put this in. Now we ran through all of the possible one-to-one correspondences that we have. And we say, oh, look, the subset of math, is it an element of the power set? Well, yes, it is. The set of math will be an element of the power set. Does the set that I come up with here of and math, does that appear in any of the one-to-one correspondences that we've listed above? Well, no, it doesn't. So that means that there's an element of the power set not in the one-to-one pairing. So there are more elements of the power set than there are of the original set. That's what this means. We go through and we find this out. You say, well, that was pretty obvious, Greg. When obviously it's not listed there, it's a member of the element of the power set. Yes, but when you're working with the infinite, it's kind of difficult to say that yes, this is, or no, it's not, because you could have one subset could be the entire set. One subset could be the entire set minus two elements. So we have to find a way that we can prove it without actually having to write the infinite number of things. So to run through this again, to make sure it's clear, this time we have the set that we've been using since the beginning, set S, that is made up of A, B, and C. And we list all of those members, every element of S down the first column. Then we make a one-to-one pairing with elements of the power set. Now, these can be picked at random, as long as you don't duplicate any, as in have the exact same thing. Again, B is in the first and second set, and that's okay because it's the set of B and C is different than the set of B. And it can include, as the third one does there, the null set or the empty set. It also can include the entire set itself. The setup is not so important, so in the homework when you're doing this, it tells you to make a pairing. Well, just make a pairing. You can make it any way you wish. Now, when doing this, we've made a one-to-one correspondence, just to list them there. We paired A with a set of B and C, B with a set of B, and C we paired with a null set. Now we're going to make a set M, using these two questions that Cantor came up with. And so we looked at the first one. Is A inside of the set that it's paired with? Well, no, it's not, right? Because A is not in, it's just B and C. So the answer is no, and then we always do the opposite for the second question. Do I want it in my set? Well, yes, because not there. I want it in my set. So I put A in my set. And we look at B and say, is B inside the set of B? Well, yes, of course it is. It's right there. So B, the answer to the question is yes. So the second question, we do the opposite and choose no. So I do not put it in my set. Then we go down to and look at the third one and say, there's C. We're looking at element C. Is it inside the empty set? Well, no, of course not. It's empty. So it's not there. Since it's not there, I do want it in my set. So I include it in my set. Now we went the whole way down through all of the one-to-one correspondences, listed every pairing, and we look at our answer. Is the set of A and C, first off, is it in the power set? Well, yes, it is. It is an element of the power set. And the second question then is the set of AC in any of the pairings that I have? Well, no, it's not. So that means after we've listed every element of the power of S and paired it with an element of the power set, there's still unused elements of the power set. So the power set must be larger. And we could do this pairing A, B, and C with different sets, and we'll always find a fourth set in this case, or more, what would prove that the power set of S is bigger than the element, and than the set S itself. So hopefully this makes some kind of sense. Now, Cantor used this argument, or this process, on the real numbers. He listed all of the real numbers in the first column, and realistically, I'm just using the reals between 0 and 1, only because that has the same cardinality as the reals. So you can use all of the reals if you wish. You can use just a subset of the reals, an infinite list of subsets. Numbers of subsets would have the same cardinality as the reals. And then I do a pairing with the elements of the power set of the reals, and you assign these as you wish, at random, so to speak. So, for example, in the first one, I had the 0.2123, then I had the set of 0.4826. I chose just one member to be in the power set, but it could have two, like the third pairing and the fourth pairing. There are two elements in the power, two elements inside of the power set of the reals, the subset that we have, and that's fine. It doesn't matter. It could have 3, it could have 10, it could have 100,000, it could have the entire set itself, or nothing, the null set in it, just like before. Now we create our set M, and we're going to put things inside of it. And we go back to the first one. Is 0.2123 inside of its paired element? Well, no, it doesn't appear there. So the second question, we always do the opposite. So do I want my list, my set? Yes, I do. Is 0.035 inside the set of its paired element? Well, yes, it's right there. We can see it. Since it is, we do not want it in our set. We do not write 0.0358. Then we're going to move to the third one. Is 0.7611 ... in the list? Close, but no, it's not. 0.7600 is not the same thing. So 0.7611 ... does not appear. So do we want it in my set? Yes, we do. So we write it down. Now we go to the next one, 0.6148. Is that in the list? Yes, it's the second one in the second its paired element in the second column. So do we want it in my set? No, I do not. Now we continue this on, and since we're doing an infinite number of times, it's likely to have more elements in it than just these two. But going through this process is just like before. Because we're doing the opposite of it, we're going to create a subset, and it's not going to be inside of its one-to-one pairing. It's harder to imagine when you're working with an infinite number of power set elements and so on, but it's just like we did in the finite. Our set M will always be one of the elements of the power set of the reals, but it will not appear in the listing, just like it did in our finite sets. So by using this argument, Cantor proved that the power set of the reals is larger, has a greater cardinality than the reals do. So while it's complex, keep in mind how you did it in finite sets, and that makes it easier to understand and follow. The power set of the reals does have a greater cardinality than the reals do. So if that's the case, how many levels of infinity are there? Well, we started with the naturals, and we've discovered that the reals had a greater cardinality. Now we discovered that the power set of the reals has a greater cardinality than the reals. Well, what could have a greater cardinality than the power set of the reals? And as you can see, yes, the power set of the reals will have a greater cardinality. Well, what has a greater cardinality than the power set of the reals? The power set of the power set of the power set of the reals. And what has a greater cardinality than that? The power set of the power set of the power set of the power set of the reals. And we can continue this an infinite number of times, right? Oh, that's confusing, right? We look and say, really? We said that back with the natural numbers, an infinite number of infinities fit inside of one infinity. And then you said that the reals had a greater cardinality than that. Yes, there's a second level of infinity. Now you're saying, well, not only is there a third level that's bigger, there's a fourth level that's bigger, and a fifth level. And if we keep going, that really there's an infinite number of infinities that are all bigger than the ones that came before it. Yes. It's mind-boggling, isn't it? They're using this argument, we can say that even though an infinite number of infinities fits inside of one infinity, there are an infinite number of infinities that are greater, have a greater cardinality than that. Surprising, isn't it? Well, it's hard to wrap our minds around, but hopefully using this process we can understand that this is indeed true. Now the homework here, the lesson hopefully helps you in reading the section from page 195 to 207. And there's not a lot of problems since it takes a little bit to set up and to get used to, but hopefully you can get this done in a reasonable amount of time. Again, the important thing is to understand the process that Cantor did. It's 2 questions, how we get the answers for yes and no for each of those columns. And then take a photo of the various questions I have listed there and email them to me.